Poi sì, io al massimo chiamo 6 ok. Io adesso vado magari a un check a vedere se io se ok, grazie mille.
Siamo super puntuali. Questo qui per sì. Questo qui? Sì. Allora, tu lo mettiamo qui, poi lo rimettiamo lì. Sì. Non lo usi? Allora, facciamo una cosa. Lo mettiamo. Un po' di acqua.
Can you hear me? Yeah. Okay, so I believe we can start. So good morning, everyone. It's a pleasure to welcome you to the closing ceremony of the 2024-2025 academic year of the Media Master. I'm Marcella Nicolini. I'm coordinator of the program as well as a professor here at the University of Pavia, and I'm honored to open today's event. Okay. Of course, we have issues. Okay. So my task here is to welcome you to the University of Pavia. We are gathered here in a place which is rich in history and in innovation. And University of Pavia was founded in 1361. It has cultivated minds that shape the science and the thought through the centuries. Alessandro Volta was faculty here. I mean, he's the guy in the picture and he's the one that invented the battery. Lazzaro Spallanzani, who is a famous biologist, or Camillo Golgi, who was a rector of this university and won the Nobel Prize for medicine. And we have been attracting the brightest minds since ever. So just to name a couple of famous students that studied here, Girolamo Cardano, who is the inventor of the Cardan shaft, which I believe many engineers here are familiar with, studied here, as well Carlo Goldoni, which all Italians study in high school. Okay, he's a playwright. This was the legacy of these giants and these bright minds, and this legacy continues today through the curiosity, to the engagement and the determination of our students and our faculty. To this end, let me introduce you to some of the numbers of the research that we do in these days in Pavia. We are proud to say that we have a strong role in granting EU funds. As you see, we had 24 Marie Sklodowska-Curie actions for around 6 million euros, 15 ERC grants for overall 18 million, and 61 collaborative projects for 21 millions. These are not only numbers, they reflect a thriving ecosystem of innovation that MEDEA students have now become part of. Let me add that I'm honored to have here one of the ERC grant holders, Giulia Fulvia Mancini, who is Associate Professor in Physics and Head of Research Laboratory for Ultrafast X-ray and Electron Microscopy, I hope I said it correctly, who will give a speech to us later during this ceremony about her research at the forefront. And let me just briefly add that just yesterday we elected the new rector, who is also a former ERC grant holder. So just to say that research is very important in this institution. These are some numbers of the University of Pavia concerning, let's say, the students and the structure of our university. We have 18 departments. 6 of them have been recognized for their excellence in research by the Ministry for the University of Research and Research. One of them is the Department of Economics and Management, which is the department that jointly organizes the MEDEA Master. We have 15 colleges, 4 of them are historical ones. We are just very close to the Ghislieri College, which is depicted here in the square next to this building. We have 18 degrees that are entirely taught in English, and all of this contributes to making this institution truly global. We have around 15% of foreign students, and all of this contributes to bring in diversity and new perspectives that enrich our academic community. This international spirit is also at the heart of MEDEA. So this is another, let's say, aspect that unites MEDEA and University of Pavia. We currently have around 28,000 students from bachelor's to PhDs. You see, we have a wide range of PhD programs, and we have around 1,100 students in master programs at the first and second level. And among these are the MEDEA students. Now, MEDEA, as you all know, is a program that has a long and prestigious history. It has more than 65 years of life. And in 2020, it has found a new home at the University of Pavia, where it became officially a university degree of first and second level. Now, I have to say that we started our collaboration at the beginning, in the fall of 2020, and starting this collaboration in the middle of a global pandemic was bold on both sides, but it was also a testament to our shared vision and resilience. And from day one, it worked. We made it work since the beginning, in spite of a completely different setting. Now, in these years, our collaboration has broadened. We have expanded the program with new courses, following the inputs of the students, new topics, and also, of course, experimenting with new learning methods. And this is also thanks to the wide range of expertise that is available here in Pavia. We have heard from scholars at top universities that have been presenting their research to us, and I believe Enzo will tell you more about the speakers that we had the honor to host this year. And I would say that together we have cultivated a program that combines the academic rigor and the real world relevance and topics that will, let's say, let you thrive in your professional future. Now, just to conclude this introduction, what is the plan of the day? So after me, there will be a video by Silvia Rappini, the CEO of Any Corporate University. Unfortunately, she couldn't make it here today, but we have a testimony from her. And then we will have Giulia Fulvia Mancini that will give us a talk about her research on nanoscale materials. Then Enzo Di Giulio, who is the Dean of the Scuola Enrico Mattei, will summarize the activities of this academic year. And we will have presentation of project works by some of our students from this cohort. Afterwards, we will have the Latella Award and then Novelli Award nomination. And finally, there will be the graduation ceremony. The reason you are here today, you receive your official piece of paper telling you that you completed successfully the master. And afterwards, we will have some light lunch outside, and we will celebrate this day together. So thank you again for being here, and let me introduce the video by Silvia. So
saluti, chiusura, quello lì perché è coperto, sì,
Good morning to everyone.
Okay, so now we will have Silvia Rappini online greeting us. So thank you, everyone, and
Good morning to everyone, and thank you all for participating in today's closing ceremony of the Master MEDEA 2024-2025. Although I regret not being able to be with you in Pavia, I am with you in spirit. On this important day, we mark the 68th academic year of the Master MEDEA and the 5th year of our partnership between Any Corporate University and the University of Pavia, to whom I would like to extend my sincere gratitude for our fruitful collaboration, which has greatly enriched the master program and benefited our students. Most importantly, today we celebrate the achievements of our 53 students as they conclude their academic year. And to our students, I would like to begin by extending my heartfelt congratulations to each of you. In today's complex economic and social context, we at Eni are committed to ambitious energy transition targets. So it is essential to leverage multiple capabilities and assets, such as technological innovation, new competencies, and a new mindset. People are a strategic value, so at Any Corporate University, we are dedicated to continuously improving and aligning our training programs with business needs to enable our people to contribute effectively and proudly to our shared objectives and make a meaningful contribution to shaping a better future. The values upon which the Master MEDEA is based, like internationality, cooperation, dialogue, teamwork, and the appreciation of diverse contributions, acquire even greater significance in the light of these ambitious objectives. And it's worth noting that the 53 students we are celebrating today come from 10 different countries: Algeria, Congo, Cyprus, Egypt, Indonesia, Italy, Ivory Coast, Kazakhstan, Mexico, and Turkmenistan. This diversity underscores the high level of internationality that is a hallmark of the Master MEDEA and Eni, and one of the key factors in the growth of our students. We aim our students to grow professionally, acquiring new skills and tools, and gaining a comprehensive understanding of the energy business, but equally important, we want them to grow as individuals, bringing passion, awareness, empathy, collaboration, responsibility, curiosity, and ultimately grow as a team, becoming also a source of inspiration for others. Our Dean, Enzo Di Giulio, has informed me that this growth has indeed occurred and the results have been excellent. He will elaborate on this shortly, but I would like to highlight a few remarkable aspects of the current academic year. Firstly, the learning by doing experience has been exceptional, with numerous projects completed at a very high level. And I am pleased to note that one of these projects has been published in a prestigious scientific journal, and others may follow given the remarkable output. And I extend my gratitude to my colleagues at ENI who supervised 13 project works this year, focusing on crucial themes for ENI like decarbonization through technology and innovation, even making the effort to measure and quantify the intangible value of innovation. Secondly, this year has been characterized by a huge transfer of knowledge through direct interventions from experts, managers, any colleagues, former students, ranging from CEOs to young alumni who attended the school last year. This intergenerational knowledge transfer is invaluable, reaffirming the vitality of the Scuola Mattei since its founding in 1957 as a community passionate about energy, the environment, and the energy transition that continues to thrive. And I'm delighted that this year students have benefited greatly from it. And to our students, we trust that in the coming years, you will support future students of the Mattei School, continuing the chain of knowledge, solidarity, and friendship. In conclusion, I wish to extend my heartfelt gratitude to everyone who made this experience possible, our partner, the University of Pavia, all the professors, both internal and external to ENI, our colleagues, the EIRL team, and our Mattei School team. Together, we have made this remarkable year and achievement possible. And to our students, you are now ready and equipped to face new challenges, and I'm confident that you will do so in the best possible way and inspire others. I extend my congratulations and best wishes for a future filled with human and professional success and satisfaction, whether in Italy or in any other country in the world. Thank you all for your attention.
So now, following the program of the ceremony, we will give Professor Giulia Fulvia Mancini the opportunity to present us her research. So, Giulia, the floor is yours.
Okay, can you hear me? Wonderful. Perfect. Yes. Okay, wonderful. So first of all, good morning, everyone, and congratulations for this achievement to all the students. And I want to start by thanking the organizers of this event and my colleagues in Pavia, the president of the Enrico Mattei School and the partners at ENI. My name is Giulia Fulvia Mancini. I will go ahead with a mixed talk in which you will see I gesture, I walk, and I pinpoint to different screens a lot. But I will try to guide you mainly through the pointer, if you can see the laser over here. So I work in physics. I want to introduce myself first. So I graduated here in Pavia. I studied in Pavia and I graduated in chemistry in 2010. And then I spent 15 years abroad. So I've been working across the United States of America and Switzerland, back and forth. And then I won this European Research Council grant, as Marcella said before, that allowed me to come back here because thanks to the wisdom of the higher ranks of this university and their good policies, which I'm sure they will be furthered within the next years with the new administration, I received the most competitive offer, and therefore I decided to reinvest approximately 4 million euros here in Pavia, where I build my labs. So today I'm going to tell you something about physics in a way that I promise you, or at least I will try, will not be boring. And the idea is that the skill set of competencies that you gained in this semester is extremely crucial for us as scientists that work in fundamental and applicative sciences, also in collaboration with industry partners, in order to develop technology that then can be deployed through different TRLs towards marketability. Therefore, we need people with your skills and competencies to deal with the problem of energy, the problem of sustainability, the problem of environment, the problem of also interfacing with policymakers, and help us scientists to help you develop these type of strategies. So today, I'm going to talk about the research that we do in my group. My group was founded in 2021, and it's called the Laboratory for Ultrafast X-ray and Electron Microscopy. So today I'm going to talk about microscopies and new forms of characterization of nanomaterials and new materials in general. In particular, I'm going to go ahead and see if I can start. Can we? Yeah. So the framework, as I told you, is microscopy. Over the decades, microscopy tools and the development of new technologies towards the characterization of functional materials has tremendously progressed all the branches of sciences that you see over here. So it's been extremely instrumental across biology, across development of transistors, chips, sensors, and optoelectronics. So it's an extremely valuable tool that branches out a host of different types of technologies. And in particular, these 3 branches that you can see over here, they are extremely interconnected with each other because, as you can see, advancements in nanotechnology, nanofabrication, not only is relevant to frameworks of optoelectronics, magnetic switching, so everything that pertains to communication and data storage, but it's also very relevant from the biological and medical therapy standpoint. So when we get towards understanding better the interaction of our body with new medicines, so it deals with the pharma industry as well, signaling, respiration, healthcare, drugs, and all of these branches are deeply interwoven and deeply interconnected with sustainability, renewability of resources, and of course with circular economy. Now, in these days and ages, we are facing one major challenge, which is the miniaturization of technology. We tend to have smaller and smaller and smaller devices that need to be more functional, more efficient, less expensive, and more performant. Because there is a downscaling of technology, so we need to have smaller objects to deal with, the scales on which this technology is deployed is extremely confined, and therefore, now there is a kind of a conundrum in the characterization of these materials, because before we were used to determine also quantitatively the properties of materials in bulk. Now nanomaterials have a very small surface, small sizes, and properties for which the models that have been developed over the years are not anymore sufficient to explain the physics and the chemistry of the fundamental processes that occur therein. And this strongly motivates solving the current grand challenge, which is understanding how these nano objects work. And in order to do this, we need to correlate the microscopic nanoscale properties to the global macroscopic functionality. And essentially, in order to do this, we need new characterization tools, new characterization methods that mark the difference in between trial and error and protocol development. This, of course, marks a huge difference in between I make some attempts in the lab to make sure that the technology is going to work, and I develop a specific protocol so that I know that my synthesis, my process, my fabrication of the solar cell is going to yield performance with 100% success. Now, problems that can be tackled with the development of new tools, such as we do at Luxem, with the development of new microscopes, problems essentially in three branches. So the first, in energy and sustainability, we are very well aware that we need the catalyst, batteries, and photovoltaics, the synthetic protocol, but also the sustainability in terms of maintenance. All these devices undergo pollution or damaging and need to be periodically maintained. So in order to maximize the process, we need to answer the question of what are the microscopical structural changes that occur when, for example, the light impinges on a photovoltaic panel. What is the fundamental mechanism that yields to the charge transport in our houses? And if the photovoltaic device lowers efficiency, why? Why does it degrade? What is the fundamental process that leads to the product having to be replaced? Other question is, how does the micro correlate to the global function? Another question that can be tackled pertains to nanomedicine and therapy. Nowadays, there are nanoparticles which are coated with molecules that can interact with our body, which I don't know if you know, but they can be used for targeted cancer therapy, because they can be designed to selectively bind to cancer cells, and then they can explode with ultra short light pulses, leaving the healthy tissues completely untouched. Now, the question here is, how can we make this type of drug delivery more targeted and more efficient? Another question pertains to nanotechnology. So in the development of new devices, the most sustainable thing that we could have is a logic gate that works like in our computers, 1 or 0, that is completely optically activated, not activated with current, but just with light photons that impinge on it. Now, the challenge is how can we do it and how can we make it at low cost? Okay, so these are questions that have in common the point that they require, crucially, the direct visualization at the nanoscale of what is happening in these materials. And so in terms of challenges, as I elaborated, we need to access the first moments in which these performant materials interact with electricity or interact with light pulses. And in order to do this, we need to take a step back and do a brief travel in space and time. So if we look at the scales in time in our universe, the age of the universe goes to trillions of seconds. So you see 10 to the 17 is so many zeros that I cannot even imagine them. And then let's go to human lifetime. The average 80 years human lifetime corresponds to 10 to the 9 seconds. If we look instead at the heartbeat, that goes with 1 second time frame. If we look at the computer clock, that would be nanoseconds, so 10 to the -9. Now we look at the fundamental processes in matter. So if we want to see the functional response of these materials interacting with light pulses, well, what happens is vibrations of the lattice of the structure or of the electrons. The lattice responds in 10 to the -12, 10 to the -15 seconds. The electrons in attoseconds, 10 to the -18. So the technology that we develop in my lab attain these temporal timescales. So they can look at the interaction of light pulses with the functional nanomaterials with a precision, a time resolution of 1,000,000 of billions of seconds, okay? This is something that we can do nowadays. Looking at the fundamental processes that we can see, let's imagine the fastest bird that can flip the wings. So that would be a hummingbird. That's an object that is a centimeter scale and flaps the wings in millisecond time frame. Whereas instead, if we go and observe the other fundamental processes, so transport, vibrations, electrons, you can see that most of the events occur at the intersection between the ultra small and the ultra fast. So the smaller the object, the faster it moves. And in this case, crucially underpinning the understanding of the fundamental physics is having a high spatial and high temporal resolutions, as I argumented before. So what's the difference in between looking at something within 1 second temporal resolution and 10 to the minus 15 seconds temporal resolution? Well, let's look at this example. This is an example of a system, for instance, made of some atoms. And if you take a shot, a screenshot, a photo, within the time frame that we have available, you see an ensemble of dots. But it turns out that if you can actually see it in motion, this vague ensemble of dots becomes actually a human motion, okay? So this is the same type of concept that we strive to attain nowadays with implementation of new functional materials. In order to do this, we utilize a method that is resembling stroboscopic photography. So if you have seen yourselves in a disco, for instance, and you have the strobo flash of a light, when you are dancing, it looks from an outer observer that the strobo is taking frames of you moving. Now, this is a stroboscopic photography that is a technology very well spread that is capable of building snapshots of the motion movie of objects that are as fast and as small as a hummingbird. But when it comes to electrons, or molecular vibrations, so fundamental processes in matter, these cameras do not work anymore. So how do we overcome the problem? We utilize pulse lasers. So lasers that instead of emitting in continuous, as you can see from this laser pointer, you have a so-called continuous emission. The laser is emitting shots, bursts of light, flashes of light that have a temporal duration of 10 to the minus 15 seconds with which we can take these photos. Let's see how we can do it practically in the laboratory. So the methodology is called pump probe. So we have, as you can see from the animation here and the figure here, a laser pulse that is emitting a train of pulses. These pulses are then divided into 2 branches. One branch is called the pump pulse. So it has the burden, the homework, the task of injecting the physical process in matter. And then the second burst of light, the probe, actually takes the photos. And it takes the photos as images, for instance, of the sample as a function of time. So just to be very clear and hopefully not boring, if the physical process that we are looking at is the apple falling from a certain quote to the floor, this is what the technology does. You start with the dynamics, so the hand releases the apple, you take one shot. Then you collect the apple again, you put it at the starting point, and then you leave the apple, pump, leaving the apple, second shot. And then you continue over and over and over by establishing a chart of time delays in between the moment in which the light leaves the pump light arrives, so the hand leaves the apple, and then the process that is occurring. So if you look at the apple falling, second shot takes another image, third shot takes another image, fourth shot takes yet again another image. Now, to be even more, let's say, comprehensive, this is an animation that is showing you practically what happens in my laboratories. So we have an ultra-fast laser that is emitting pulses. So you see that the laser pulses are on one side in blue and on the other side in red. The red is the pump, so it's starting the physical process. The blue is taking the photos. And these are short bursts of light. So you need to imagine that you have one after the other. Now, in the process, you see that the red light is entering an experimental chamber and it's injecting the physics in the material contained therein. And then after a while, the blue pulse arrives and takes the photo, and the photo gets to be collected at the detector. And you do it over and over and over and over, and all with all these frames that you have collected, you can create a movie of the system that is evolving through time with a spatial resolution of nanometers. So it's more than billions of meters, and the temporal resolution of trillions of seconds. Now, there is a fundamental relevance in what we do that has also been recognized through the decades with some key Nobel Prizes. Interestingly enough, this type of technology implementation is extremely interdisciplinary. So I'm a chemist, now I am in a physics department, and the people that have developed this type of technology were first awarded with Nobel Prizes in chemistry, particularly very first studies awarded the Nobel Prize in chemistry in 1967 for utilizing flashes of light to look at reactions, chemical reactions happening. And then in 1999 for utilizing this laser technology to look at reactions injected by light, awarded to Ahmed Ziweil. Afterwards, laser technology underpinning the implementation of these techniques was awarded the Nobel Prize in 2018 for, as you can see, the development of methods generating ultra-short, high-intensity optical pulses. And only 2 years ago, another Nobel Prize for the attosecond for developing new tools that allow to explore electrons inside the molecules and atoms and see how energy or charge moves inside the materials, okay? So these technologies that I showed you crucially rely on the work of these Nobel Prizes, and particularly the technology that was developed by Pierre Agostini, Ferenc Krauss, and Anne L'Huillier is the one that we have in my laboratories, starting from which we develop the methodologies that I mentioned before. So now let's get to these techniques very briefly. So starting with the electromagnetic spectrum, the one that we can grasp with our eyes is the visible region. So it's a very narrow region, okay? The one that we utilize is the one that branches to the ultraviolet and the X-rays. The X-rays to an energy that is comparable to the one that we have in our hospitals for taking radiographies, for taking CT scans, and so on and so forth. So because we have done probably some radiographies in our lives, we know that the radiography does what? It allows to see through the person, and this is an assessment of the penetration depth, the penetration capability of these rays to soft matter. So this type of probes, these X-rays that we use in my laboratory to implement microscopes are very important because they are available in pulse sources, so we can look at dynamics. They can penetrate matter, and so we can rebuild the morphology of the materials in 2 and 3 dimensions. And also, they are very specific to the type of element. So if you want to understand which type of chemical species you have in your body, in principle, you can do it. So the type of pulse sources that we utilize in my lab are 3. One is heavily relying on the achievements of the previous Nobel Prizes, and other two that are synchrotrons and free electron lasers are large installations, large-scale facilities, for which you need to apply for a call to get beam time, because the beam time, 1 week of machine time in these devices can cost up to 5 million euros or something like that, okay? But we do not only rely on this type of tools, but in our lab we have this, and particularly we utilize these cutting-edge technologies, so short light pulses, to look at the fundamental processes in the nano world, of which now I'm going to provide you briefly a couple of examples. Just to contextualize a little bit the effort, the relevance of this type of technology not only is assessed by the Nobel Prizes being awarded that I showed you before, but one thing that I wanted to mention is that whatever you see being, very laser-based, physics-based, in reality branches out not only across countries, but also with companies. So at the moment, I'm working actively with 2 laser companies, one industry that makes optics for aerospace, and one industry in Canada that makes detectors. So this is to say that even if the research can be deployed, the research and innovation at a very fundamental level and or applicative level, the contacts with industries are at all times extremely important, and that's something that we encourage and that we actively look for. And that it has also been consolidated by a couple of European, and actually this is an international network that is based in the United States that I am a representative of. So systems that we look at and challenges, in particular, we focus on nanoparticles and assemblies of nanoparticles. So objects that can be very, very small and that assemble together. They can develop hierarchical structures, and we want to characterize them, understand them out of equilibrium by implementing new microscopy tools. And by doing so, we develop also new microscopy technology. So in particular, the objects that I'm telling you about that tackle all the open questions in nanomedicine and therapy, energy and sustainability, nanoelectronics, and so on and so forth, are very small objects, you see. They have a size of 10 to the -9 meters, so they are very, very small. And they are characterized by a core, a structure, an inner shell that is made of a metal or a semiconductor, but then they get to be functionalized with a coating shell of organic molecules, which can interact with membranes and that interact in drug delivery, for example. Now, these objects are very tunable in terms of size, shape, and functional response. And they have very interesting properties, not only of tunability, but also of collective responses. So just to give you a couple of examples of where these systems can be used, this is a work in which you can show that by functionalizing properly the nanoparticle, you can permanently inhibit and destroy a virus. So what you are seeing here with microscopy, no less, is that a particle that is properly tailored attaches to the virus and then in a few minutes leads to its explosion. On the other hand, these materials can also be used to coat aerospace devices because they have a very high resistance in terms of thermal and mechanical resistance, and the properties ultimately depend on ligand chemistry. So the aim here is to visualize both the large scale and the functional response of these small objects, where you can see that here, these are simulations. The challenge is to develop microscopes that can look at these in real time. tackling the difference of response in time scales, composition sizes, and so on and so forth. So for this, the microscopy is a little bit unusual in the sense that we are used to working with microscopes like this, right? That are very compact, very small, they can sit on a table. Now, with the type of radiation that we utilize with X-rays, there are no lenses available. So the best strategy is to remove the lens in between the object and your eye, and to replace the lens with a computer that forms the image through a computational algorithm. So it looks at the information that you have, and it so-called reconstructs the image. Now, I don't want to get too much into the details, but you saw how the microscope, the tabletop standard microscope looks like. This is instead how our microscope looks like. So it's a bit different, right? It's 4-meter based. This is the most efficient and marketable device that is existing in the world at the moment, but it's not deployed in 30 by 10 centimeters. It's 4 meters by 1.5. So, but we are getting there. So what can we do with this microscopy? Let's get to a couple of key examples. One thing that we can do in nanometrology is the following. So we have a transistor, we have a chip that has been fabricated, and then for some reason, the fabrication presents lift-off defects. And you don't know which type of lift-off defects there are. You don't know how you can make your synthetic and production protocol better. So you can put this device under our microscope, and with just one image, we can tell you the chemical composition of the material. We can tell you with a very fine detailed precision if there have been production defects, and even we can tell you if there have been oxidation processes or pollution processes or you know, any type of chemical process that led to the pollution of the device. And by looking at the device in just one shot, one image, we can instruct you on how to make the production a little bit better, improved. Now, keep in mind that typically, for an image like this, you need to use approximately 3 or 4 different techniques. This instead is an image that is quantitative and non-destructive, which is not trivial, taken in just one experimental campaign. So not only the characterization methodology is cost effective, but it provides an information basis set that is orders of magnitude higher with respect to the standard protocols. Another last example that I wanted to provide pertains to this particular case because the applications can be many. And and for this, I recall one demonstration that I did before I came back here when I was in the United States. So as you can, as you probably know, in the United States, at least back in the days, partners that could finance research were the Department of Energy, the National Science Foundation, and the Department of Defense. And so we were approached by an agency of the Department of Defense that was interested in understanding if this type of technology could be used to monitor in real time chips that were coming from abroad. Because sometimes there are, you know, some chemical elements that are not particularly healthy, or there is a production that is incompatible with European or American compliance protocols and so on and so forth. And so they said, you have this technology, can you make it so that we can look through the material, through buried layers, and actually see what happened at the interface? And so actually the answer is yes. So the demonstration that you can see here is an identical twin sample, one that is not coated. It's a chip of copper on top of a silicon dioxide substrate. And then you have the same sample coated with a thin layer of metal. And if you look at it in a standard microscope, you see that this looks like a mirror because you cannot see at the interface, right? So what we can do with this type of microscopy is actually creating images that are quantitative and non-destructive of what happens at the interface. So the image that you're seeing here, is actually what's happening in between this part and this part. It's at this interface. So we are looking through the metal. And because you can see that there is a difference in contrast in between one image and the other, what we can actually do is to tell you that during the evaporation process that led to the deposition of this layer of aluminum, there have been chemical reactions occurring which damaged the interface. And we can quantify it by telling you in a non-destructive way that the copper has oxidized to form a certain amount of different oxides, and that there have been interdiffusion processes which led also partially to the damaging of the surrounding silicon dioxide. So this is something that can be easily deployed for nanometrology, for inspection, and in a host of different possible branches, let's say. There are also many other different applications. So the one that I'm showing here very briefly is the opportunity to look at objects that are too big to be simulated from first principles. This is a nano antenna that is inhomogeneous. And by using this type of microscopy, we inject thermal response in the object and then take photos and understand how the physical fundamental process occurs in different time steps. And there are also many other applications that I don't want to bother you with right now. Applications that I want to mention, for example, for the characterization of the fundamental processes in materials used for photovoltaics. This is a material that now is widespread. It's a perovskite that is very extensively researched for being a prospective candidate for new solar and photovoltaic devices. But the fundamental physics inside, so what happens when the light hits the material, how the material rearranges to accommodate the charge and transport it to the electrode to our home, was elusive. Furthermore, it was not clear if the interaction with the light was also associated with a thermal response. So in other words, is the interaction with the photons completely clean, or when the light impinges on the material, you have heating as well? So with these techniques, we can disentangle the two responses. At the top, you see curves of response from heat. At the bottom, you can see responses from the process induced by light only. I don't want to bore you with the details of these curves, but you can see qualitatively that these curves are different, which means that the two processes are completely separated. So the photo-induced process and potential degradations that come afterwards come from separate different triggers. Light does one thing, heat does another thing, which was very instrumental for developing the protocol of this type of materials implemented in realistic devices. There are also other perspective, let's say, applications, and I want to leave you here, and I'm concluding. Thank you for your patience. I'm concluding here with telling you that the technology is already mature to move it towards the all-optical switching and the control of magnetic topologies, as I was mentioning at the beginning. It is possible nowadays also, and the frontier of sciences are moving towards the possibility of utilizing clean light pulses to control magnetic responses and topologies in the material and actually guide these processes towards device making. And also new routes towards targeted drug delivery are happening as I showed you before. So in conclusion, I want to leave you in reality with a quotation from Professor Mildred Dresselhaus that summarizes a little bit a few key cornerstones of our research and also of what I showed you in this presentation. The first is that when the objects become smaller, the properties change heavily and everything changes at the nanoscale. The second is that in order to understand these changes, we need to understand the so-called structure properties relations. And for this, we need the new characterization tools that can guide the processing, the productability, let's say, of any type of material beyond the trial and error. And ultimately, let's say a couple of food for thoughts. The first is that, as you can imagine, developing this technology is extremely challenging. So the inspiration to keep working is fundamental. But this is not only in my case, this is also a token for you guys, because now you are getting to the job market, right? So never lose inspiration. Inspiration, drive, and motivation, whatever you do, is ingredient number one at all times. The second, and I'm really glad that Marcella mentioned it, I would like to remind that it's beautiful that in this room there is an extremely high level of diversity in terms of cultures, in terms of gender. And I also want to stress as a mentor in science that this is a value that particularly in these times that are very challenging, we should never forget. So I really hope that you harnessed the experience that you have, because having had the opportunity to work in a multicultural environment is absolutely invaluable. So with this, I want to thank you, and I want to thank my group, and of course, the funding agencies. And I hope I didn't go too long, but thanks again for the invite.
Well, let me just thank Julia for the very instructive and inspiring speech. Thank you so much for your words. And I have to say, we are proud at University of Pavia to have colleagues like you that are at the forefront of research and that are mentoring students as you are doing. So thanks again. And now I leave the floor to Enzo Di Giulio for the presentation of the activities of this academic year.
Thank you. Can you hear me? Yes. Okay. So wonderful presentation. Bellissima. So welcome. Good morning. It's the final day, final speech of this long journey. Traditionally, I go to present what we have done this year. And usually we start with performance. But before this, I want to quote something that happened yesterday in the school, in the corridors, and I was in the area of the coffee machine, and I met Sergei Shulga, and so he started to talk about this year, and he said, "Oh, so this is a very fantastic year. So this is the best year of my life," and I think that and I think that for us, for professors, this is the best reward that a professor can get. And then he went to comment about is growing. Also, our CEO referred to this growing, the growing not only by acquiring tools, competencies, but the human growth. This is very important. And they said And here there is a special relationship between professors and students, and is, let's say, horizontal. So I was not used to this. And I think that this is a peculiarity of the Mattei School. No? So there is this community. Our CEO referred to this community of people passionate in energy, no? And this is something which now you are in. And while I was talking with Sergey, I took my smartphone and I went on WhatsApp and I showed him the meeting of the students of 30 years ago. And in this meeting, there was the ambassador of Kazakh in Italy, no? There were people that thought to you, like Andreas Steger, for instance, president of the International Gas Unit. So this is the Scuola Mattei. There is a community of people that interact, stay together, and gives a contribution. Now you are here, and I am sure that you will give a contribution to, of course, the context in which you will work, but again, also to the Scuola Mattei by, for instance, supervising projects, for instance, giving lectures, for instance, talking and mentoring our students. Having said this, let's go to the performance. Okay, so a way for having an idea about the year is to look at the results, the marks of the exams. And so it's not easy because anyway, the yardstick can change, the professors can change, but however, that is a reference. So what we do basically is to take the average of so this line here is the average of these they are, I think, 12 years. And here there are different periods. So if you go back here, there are decreasing trend, then there are increasing trend. You can see here an increasing trend. Then this is the COVID period, no, which is not measurable because, I mean, the exams were done in different way. Then we have two good years, 22-3 and 23-24. And now this is your turn, and this is your result. It is exactly like last year, 88.1, which is, I would say, a very good result, as I show you in a moment that this result comes from different performances in the three phases. And you can imagine which phase was better and which phase was the worst, but we will see this in a moment. Another important aspect is the standard deviation, because the standard deviation distance by the average give us an idea about the homogeneity of the class. And so it is a pleasure to see that this year was very, very homogeneous. This is the lowest standard deviation ever. Another comparison that we go to do, and we usually do, is the female-male battle. And so there are periods in which females are better, males are better. And we come here from, I think, 5 years in which females did better, but this year they still did better. So, and since we were talking about gender, so this is, I mean, another testimony of the strength of the women. Having said this, this is your performance. And you can see here what happened in the three phases. Fortunately, we had just three phases, not the fourth phase. And probably there was a placement effect with a negative discount rate, so the future was more important than the present. Probably there was the spring, you know. So, I mean, some efforts here played a role. However, globally, so the result was very, very good. Our journey, let's recap our journey. We did very many things. So we didn't start well because, okay, after the recruitment that was done also by us together with our colleagues of Airline International Resources that also care about your placement, as you know. So that was not easy because, I mean, recruiting, I mean, a lot of engineers and economists, top level, more than 105 mark in the degree, so it's not simple. So then you came and you remember this was your first day. So that was your first day and there was this fire. So we were expelled from the school and we went out. And so you returned 2 days after. Then we started with the team building, you know, a lot of activity, team building activity. And team building continued in Como. So this is the very nice visit of people, of students of first level to Luciano in Como when he had this problem with his knee. And so this is the train building. So the train was built by Luciano. So this year we continued our strong focus on energy transition. We are used to saying these last years that this is a master on the energy transition. So a lot talking, developing, studying energy transition. We do this in many ways, of course, for giving 2 main points of the workshops by Stefania Migliavacca, Sea Road. So these are moments of the Sea Road workshops. This is the final result. You can see you arrived to 2.5 degrees Celsius. That was your result in this role play. Then there was arrows, so the simulation of the policies, and this is something that you did. And another thing is the course in renewable economics. We probably gave you a quite different idea about the power of renewables, you know, because we focused a lot on the criticalities of renewables, you know, and so there are a lot of barriers, let's see, but it is nice to have a professor like Federico Pontoni that is very, very open to the growth of renewables, and he stresses the strength points of renewables. And this is your last visit to Venice, no, the biorefinery. This biorefinery was the first biorefinery in the world, the first one to be built. And then this is something that we are proud of. Because so this year, Beatrice Bragato pulled out from her head this workshop. So that is the first time that we proposed this workshop. So they were very, very appreciated. We'll continue along this line and the long line of diversity, inclusion, and I mean, focus on gender issues. But I mean, Scuola Mattei, we talk not only about energy, environment. So these are works done in the Luciano's course first phase. You can see Titanic, the price of surviving, an economic analysis, or the Marvel economics, or the Taylor Swift economics, or the economic behind filmmaking, or why Disney acquired the Star Wars franchise. So these are different perspectives for which to see it, interesting things, phenomena of life. And so there is not only energy within the school, but also, I mean, something that broadens your mind. Learning by doing is a key aspect. So we always try to push on learning by doing to make our students working. So they have to work because by working they learn. So as you probably remember or no, I don't know, when we started the academic year during the ceremony, I quoted this number. So today we have this target. That is, we want to do at least 175 works. And so we do not control this number during the year. We just control it at the end. So we do our work. And so this year was not easy because, I mean, in behavioral economics, we did have some works. But however, counting, I mean, courses, I mean, jobs, works done in other courses, the result is 175 exactly. Exactly. And so this is the list of your work. And here I did not calculate the Marcella works because you have done a lot of presentations in our course. So it is, I mean, for homogeneity with the other years, not calculated. But here you have also the voluntary works, for instance, the geopolitical debates that you have done with the students of the last year. The article we published, the booklet by Manuele Mirabella, a very nice synthesis on energy transition. So all this is calculated here. So let's see something that you have done. So project works, I will not show all the 175, but I mean something must be showed. So we start with gas market, Italian, French gas market. So just for giving you an idea. So that is the Nexus water, energy, food in South Sinai. This is the business impact of innovation. So today, this year, we worked a lot on innovation, patents, and knowledge. This is with planning to the analysis of storage assets bidding strategy in the Italian power markets. This is the knowledge management system, the work that was supervised also by our colleague, Costantino Alberici. And this is risk evaluation in the oil and gas field, one of the traditional fossil that remained in this new flow of projects that are mainly devoted to, I mean, climate, decarbonization, and so on. This is the agrivoltaic, so how to use solar energy in the agrobusiness, let's say, corporate entrepreneurship, so what can be done within the at the corporate level for entrepreneurship, the issue of innovation that returns, how we can valorize the intellectual property, and the data center market in Italy, analysis of data center market in Italy with reference to power supply, and then oxy-combustion power plants in Italy, and the cannibalization of solar power, that is with Fondazione Enrico Mattei, and this will be presented in a few minutes by Teresa Chazaro. And the innovative oxy-combustion power plants, that is another project that was done with any technology department that will be presented in a moment by Jacopo Pietraroia. Models, many models were done. I quote here what we have done with Stefania. You remember probably your models about China, dual carbon challenge, then nuclear energy and data center in the US, the European Union, the ban of gasoline diesel cars in Europe, hydrogen. So they were done. We did some works on hydrogen. Indian power generation sector, so they have some problem with electricity, mainly because of this big boom of air conditioning devices. Again, the ice ban in Europe, transportation, hydrogen. Again, this is within the European Union. Nuclear energy in the US data center. So the topic of data center and the need of a lot of electricity was well developed this year. So we did many works on this. tutorials. So you did tutorials in energy transition, and let's see something hard to abate sectors, how to abate emissions in sectors where it is not easy. Electric versus traditional cars, a comparison. That is the problems with wind energy, negative prices, problems in the profitability of the wind sector, climate change impact, so migrations, so new problem. CCS and CCUS, this is something that is very important for Eni and is investing a lot. And I think that some of you will work in the future years on this state of the world climate finance, okay? Very, very important. The topic central to the last COP29. Fission, nuclear energy fission, but there was also nuclear energy fusion. So these are some works that were done. SDG, some focus on some very important sustainable development goals. So the debate between OPEC and International Energy Agency about the future energy scenarios, and then many conferences. So we did many conferences this year. I show you something. So Luca Bertelli came twice by talking about geology, and then returned to talk about the oil and gas business and what is happening in this sector. Alessandro Lanza also came twice. This is for the Italians. And once in talking about the Mattei, and then I returned to present his book, The Century of Energy in Italy. Gonzalo Cabrera, our former students, came from Spain, an expert in hydrogen mainly, but not only. And then we had two former students. You remember Daniele Morricone, that is a former student of ours. He talked about batteries, he's CEO of Zero, and Francesca Gostinelli, CEO of NLX. Andrea Steger, very long conference. It was a 3 hours and a half conference without any pause. Our former student, Lame Verre, she was from London. Now she's director in Net Zero. Matteo Terevazzi works in ADNOC. He talked about, the business of oil and gas in Middle East, what is going there, on there. And we had also some theater, that was for the Italian, but there were also some foreign students watching this event, I Cappelli di Vanguard. It was about environmental communication, how to communicate nicely the environmental aspects. And then the wonderful webinar organized by the University of Pavia with the top researchers, Francesca Truffa, Michigan Ross Business School, Raffaella Sadun, Harvard Business School, Du Young Kim, Boston College, Gemma Di Poppa, Brown University. And so this is something that adds a lot of, quality and high-level teaching, information to our master program. But in our conferences, we talked also about football. So Luciano was able to bring the CFO Parma Calcio, Valerio Casagrande, the CEO Como Calcio, Francesco Terrazzani, and he was also able to bring Davide Caranchini, chef of the restaurant Materia in Chernobyl. So this is an aspect of the school that is very important for us because it enlarges the horizon. So we talk about energy, so environment, energy transition, but it's also important to enlarge your through this event. Publication. So of course during the year we write. So I think that we publish quite a lot at different levels. Can be dissemination articles, can be scientific articles. Here there is something just for giving you an idea. So the article by myself and Stefania at Zero Then there is one of the different articles by Beatrice, this is Linguaggio Identità, and there is Luciano that writes books as we write articles. So while we write articles, he writes a book. So this is the last one, no? No, there is Pizzico di Economia. No, this is the last, okay, but there were two books, I mean, more or less, Pizzico di Economia and Economia. And there is this is very important. I mean, this is, I think, yeah, that was supervised and coordinated by Stefania, and it is an evolution of one of the model in system dynamics, no? And so it is very, very interesting that, and we are proud of it. So I mean, to have an article published on a leading journal like Energia, it came out just, I mean, a week ago, maybe less. Then they do a lot of things. So my colleagues, they do a lot of things. So videos, so these are some of the videos by Stefania. So Stefania does also a lot of teaching, dissemination with workshop, climate simulations, a different level, a high level in can be summer schools or in the school also, no? In the high school, so with young students. Okay, Luciano is a strength of nature, so he is very, very strong in producing. I don't know how how can he produce so much. So maybe he does sleep. How we don't know the secret. However, you know him, so if you follow his page in Instagram or TikTok, I don't know, so you can follow Luciano. At this point of the journey, usually I say something on the international context, so something that is so high level, something that I will not do this year, because one is boring, two, the international context is not so nice. Let's see if it improves, no? Let's see if it improves, but I mean, it's a situation quite strange, and so you wake up in the morning, there is a war, a couple of days after, now there is the peace, so it's a schizophrenic situation. So I will just say something about this human journey. So we always stress this human factor, so the human improvement. This is important. And here I've stolen some pictures by the Elena Rossi videos. So there are ways for stealing. Stefania told me how to steal anything with a device. A human adventure. So that was the beginning. So that was the beginning. So with the fire, so there was an evacuation. And that was the reaction of the students. So that was the reaction of the students. And I think that, I mean, the nature of this group of students is in this picture. I mean, so this smiling and fun aptitude, so that is very nice. And I was with you during all the year, no, by doing works in our classrooms. So this is the opening ceremony, you remember. So this is with Gonzalo. And so this is Christmas greetings. This is the Pink Wednesday. No, that is Pink Wednesday. So I didn't know about this activity. Luciano told me that he was able to understand what it was. That is the biorefinery visit, the day and the night. Then there is also a race, but I will not show the race front of San Marco Church. So that is amazing during the night. I will not enter into the chapter of happy hours or dinners or lunches, because that would take an entire day, you know. But I saw from that video that you had an intense activity, in this context. Let's go back in the classroom. So the classroom was a place for, following, attending lectures, for debating, no? So we did several debates this year, for taking exams, for taking exams, a way for talking about football, the class as a way for producing something tangible, for reflecting. That was, I think, project management. And the class is something to avoid, and delaying. So let's say, that was put there by Elena. So it's not me. So let's say that we had some problems in this contest this year. A way for living, stay together, with this wonderful Baba. And that was a new entry, something that we didn't have in the former years, because I always tell the students that the classroom must be for you a gym, something for doing mental gym. But this year it became something for doing physical gym. And we didn't have ping pong. And ping pong grew and grew, so there was a championship. Then we had to stop this because there was this ball, tick-tock, that was noising for our colleagues. So that was our journey. Here I want to thank all you students, that made this possible. So this is the picture in the first day. I want to thank the University of Pavia, of course, Marcella, and all the university. It's a wonderful cooperation. It's a cooperation among friends, I would say. My colleagues, I would like to give a clap. Beatrice, Stefania, and Luciano, and all the professors, that teach in the school, or any. So any is a big effort for any. So when we call former students to teach, or any colleagues, we know that it is not easy for them. And we will call also you in the future. So you will be busy with your job, and so you have to prepare a lecture for the math students. So that is something. And so we thank this Eni for this. So the professors and our colleagues of AIRL and International Resources for the wonderful job they do during the recruitment and in the placement. The placement was very good this year. There were some, unforeseen developments, but I think that they fixed the problem very, very well. So that is the first day, a tidy class. That is the last day, quite relaxed class. And it's not the last. And this is the final Big Bang. So I think now you are ready for going and for entering into your new life. Having said this, so something it was quite it was quite on time. Having said this, now there is something more serious. Someone more serious than me, and we go to the project wars, and the first one is Teresa. Teresa, you can come here, no? Teresa. Me li facciamo prendere sulla... Per stare lì, ci giriamo. Ah. So this project is done by Teresa Ciasaro with Vittoria Nelli, Stefano Mangioni, Yuri Martinelli, the cannibalization of solar power.
Good morning, everyone. This is a project that we presented as a funnel project. We already mentioned the team members, Anelli Vittoria, me, Teresa Ciasaro, Mangiore Stefano, and Martinelli Yuri, with the supervision of Matteo Manera and Federico Pontoni, which were two professors during the master. So let's begin. I promise I'll try to make it brief and digestible. So the topic is the cannibalization of solar power and its impact on market value and econometric analysis. I know it's a handful, but it's easier than the title seems to be. Technical issues, guys. Okay, we are back on track. So the first question that we need to ask, or well, people ask when we talk about this topic, is what is cannibalization? Okay, cannibalization effect refers to when a renewable source, especially solar, tends to produce or overproduce during a particular time of the day, especially the middle of the day. This is what we call peak hours. So this increase in production is not particularly met by an increase in demand, which makes the prices go lower, which means that solar is not as profitable as other sources. So this study was based in 3 countries, Spain, Italy, and Ireland. These countries were selected because each one of them have a very particular energy mix and a different percentage in solar and wind. In the case of Spain, we have the most participation of solar into the energy mix, so the cannibalization effect is more severe. In the case of Italy, we have a more balanced profile with not so much integration of solar. And then Ireland was added as a control case to see if we can see this effect also in wind, because previous studies have observed it in solar, but no previous study have tried to observe if it happens on wind. And the objective was to measure this cannibalization effect and, as I mentioned before, to see if we can see in the wind production. So moving on. So for us to measure the cannibalization effect, we used a key indicator that is known as value factor. So in simple terms, value factor is just a ratio that tells us out of the average price by day for energy, how much the energy produced by a single source can capture that price. So let's say that, for example, just to give you a number, let's say that every unit of energy in a day is 10 euro. So we can have 3 different scenarios when the value factor is greater than 1. This means that if the general price is 10 euro, then this source earns 11 or 12. And it's usually when we have sources that can produce when we want to, so they produce when the prices are high. The second scenario is when value factor equals to 1. This means that if the general average price for the day is 10 euro, then the source earns 10 euro. So is this usually for sources that produce throughout the day? Let's think, for example, nuclear. And the third scenario, which is the worst economically speaking, is when value factor is less than 1. So again, if the general price for electricity is 10, the source earns 9, 8, or below. And this happens because the sources produce when the prices are low, which is the case of cannibalization, and it happens for solar, and we will observe if this might happen with wind. Okay, to move on, the way for us to make the study, again, we decided to use the key indicator of value factor to measure the cannibalization effect. And we tried to see the correlation between the value factor with generation and sharing energy mix. So we tried to measure from the production side and the integration when you compare through the whole energy mix of each country. And of course, for us to try to capture all the dynamics between the energy markets, we had some agents of influence. Some of them are the electricity supply, electricity demand, We also included foreign prices, the French price for Italy and the UK price for Ireland. We also added monthly and intra-week seasonalities. Just consider how much the patterns of consumption can change from summer to winter or from a Wednesday to a Saturday, for example. And what we call lagged variables, these are used in econometrics to bring a balance to the model and also to see how much dynamic the interactions in the energy market are. So the results. Okay, so it's important to mention that on the electricity supply, depending on the source that is producing is the effect on the value factor of solar. So the cannibalization effect on solar was observed in both Spain and Italy. This means that for every 10 gigawatt hour that it's produced in a day, the value for solar, it's reduced 2.5% in Italy and 1.9% in Spain. And there's effects called cross-cannibalization when one source produces affects the value of another source. So in this case, if wind produces, it also affects the prices of solar. And we also have positive correlations. So if we have a base load source, which has sources that produce continuously throughout the day, like nuclear, then it balances the production profile, and it also can improve how much the value of solar is. So for the demand, as I mentioned before, the cannibalization effect is because we have higher production that is not exactly met with higher demand. So of course, if we increase demand, we increase the value of the solar energy produced. And for cross-border influence, it's positive. It makes sense that if the main countries where we make imports and exports increase their prices, then national prices will also increase. And for seasonality, I think this is very logical. On the winter, we have the most reduction or the most cannibalization effect in solar. This is due to the fact that the peak hours of the day are not usually when people tend to use more electricity. And in summer, it's when solar really shines, because when it's the hottest part of the day is usually the middle of the day, which is the peak hours, which makes the demand for cooling make demand meet production, which is good. And for intra-week patterns, again, logically speaking, when we have the working days, Monday to Friday, we usually have activities in schools, in works, in industries, so they meet the production. And in the weekend, we have a really, really bad cannibalization effect due to the fact that people usually don't work or have a lot of activities during the peak hours. And so for the second objective, which was to see the effect on the wind, okay, spoiler alert, there was no cannibalization effect. Trend forecasting, what this means that, as you remember, we tried to use different factors that could affect the value factor. But in this case, wind, at least the factors that were selected by us could not really forecast the trend of how value factor behaves in wind, which means that might be a more complex structure than we thought. The self-cannibalization effect was not observed in neither of the countries. And seasonal effects were either non-existent or very weak. Another important opinion is that there's also a cross-cannibalization effect. So if we produce solar energy, it also tends to affect the value of wind and vice versa. Particularly, this effect was seen in Italy. And in Spain, there was a strong presence from lag variables. To not go into the technicalities, this means that there's very, very dynamic market. So there's like a lot of changes in Spain, particularly for the prices of wind. And so to close for the key takeaways, solar faces significant value erosion. This means, in other words, there's a very strong solar cannibalization effect in all three countries. And there is also a presence of what we call cross-cannibalization. So when we use other renewable sources, it can also affect the prices of each other. There is no significant cannibalization effect for wind. And maybe other type of interactions or factors need to be considered within the study to really understand what are the transit prices for wind electricity generation. market structure, and mixed matter, because each country, of course, has a different profile in energy making, but it's not only the amount of energy produced by solar, but how much that amount represents of the total production of the country. So it's not a matter of total production, but a matter of how you distribute that production for the entirety of a country. And last, demand is key to mitigating cannibalization. As I mentioned before, this effect is because you have a production that is not met by demand. So the best way for us to avoid cannibalization effect and keep using renewable energy sources such as solar is to try to make production meet demand, either through policies or through technical and technologies approaches. So that's it. And thank you so much.
Thank you. Thank you very much, Teresa. Thank you very much, Teresa. Now it's time for the second project, Jacopo Piedraroia. This is a project on innovative combustion power plants done with Maddalena Mariani, Sergei Shulga, Giorgio Torraca.
Everyone, I'm Jacopo, and today we'll present the project that I carried out over the last few months with my colleagues, Maddalena, Sergei, and Giorgio, concerning innovative oxy-combustion power plants within the Italian electric market. So we will have a look at the context, the technology, and the objectives of our work. We will then assess the cost competitiveness and the investment feasibility of this technology. We'll then compare it with the main alternatives present on the market, and finally we will get to the conclusions. So let's start from the context. We all know that we have important climate and energy transition targets that impose a need for dispatchable and low-emission solutions. However, the system imposed some constraints in the form of intermittency of renewables, alternative gas turbines, which emit heavily, and the carbon capture that is particularly costly and limited in its application. In this context, basically, our technology can represent an important opportunity for the system. It's called SOS CO2 cycle plant. Here you can see a schematic representation of the process behind it. It's basically a common gas turbine, but with the specificity, so with the advantage of being dispatchable and scalable, but with also the aspect of being highly efficient and to have an integrated CO2 capture system that allows it to capture up to 95% of the emission it produces. So given, of course, this space of opportunity created by this new technology in meeting our needs, our goal was twofold. Actually, our project was divided into parts. The first section was aimed at assessing the competitiveness and the financial viability of the investment by modeling the CapEx and the OpEx, so the cost structure behind the technology. And secondly, to compare the technology with the main alternatives present on the market in two cases of business models by modeling the revenues based on real Italian data concerning the market, the electricity market. So let's go with section one. We initially started from a baseline plant of 80 megawatt. Here you can see listed the main costs composing the initial investment. As you can see, among the capital expenditure, the most significant one is the one referred to the so-called solid oxide fuel cell, also known as SOFC. It's not just the most important in terms of cost, it's also the most innovative, and subsequently, it's even the hardest to be predicted. So in order to deal with this problem, we basically created scenarios. So a low cost, a medium cost, and a high cost scenario for the SOFC. And then we also scaled the plant, not only using the baseline of 80 megawatts, but also adding a 150 and a 50 megawatt scenario. As you can see, the baseline result here is 493 million euros required as an overall initial investment, but it's part of a broader range of results that go from a minimum of 295 to a maximum of 1 billion euros. If we divide these results by the power of the plant, so we can see that the most convenient solution here is the one suggested by the 150 megawatt alternatives. meaning that taking the capital expenditures per megawatt, this is the solution that would allow to save more costs. Another important piece of information is the lifetime of the SOFC, which requires to be substituted every 7.5 years. This, of course, would increase the overall costs for the investment, and this will, of course, we will see, play an important role in the financial feasibility. Concerning the operative costs, we have 5 main items: the fuel gas inlet, the CO2 net emissions, the CO2 transportation and storage, operations and maintenance, and labor costs. Again, here we have 9 different scenarios. And again, we can see how the 150 megawatt solution in terms of size offers the lowest cost per megawatt in each cost scenario. This is, of course, due again to economies of scale. Everything we said so far is actually synthesized by this measure that we use to assess cost competitiveness. It's called LCOE, or levelized cost of electricity. As we can imagine, basically, the LCOE tells us that the most convenient solution is the 150 megawatt one in all the 3 different cost scenarios that we created. You can see here. And another important information here is that these costs, per megawatt hour of the electricity produced through these technologies, comparable with other blue power, with the one produced through our blue power technologies. Concerning the financial viability of the overall investment, we use another measure that is called the net present value. Basically, this measure tells us that there is no situation in which the investment seems to be positive. So, in other words, the investment overall is not financially viable. So let's go to section 2. Here, the objective was to simulate and compare the hourly net revenues over an entire year to assess if the SOS CO2 cycle, namely our technology, can surpass traditional CCS-based solutions in 2 different revenue scenarios. Basically, the 2 scenarios are case A, also known as merchant, and a case B, that is the peaking scenario. In both cases, we compared our technology with the main competitor, which is a combined cycle gas turbine for case A and an open cycle gas turbine for case B. In both cases, of course, we talk about alternatives having also the carbon capture, because we talk about blue power competitors. In the first case, we used a power size of 400 megawatt. In the second, we used a 100 megawatt power size. And there is also an important difference in the revenue streams that we used in both cases. In the first case, they mainly come from the so-called day-ahead market, which is the main electricity market that we have here in Italy. And in the second case, they come in the form of a fixed premium from the capacity market, plus eventual additional revenues in the form coming from the ancillary markets. Basically, we computed the net revenues, making a simple difference, the difference between electricity revenues minus 5 main operative costs. And the 5 operative costs are the ones that we saw before. So again, fuel gas inlet, CO2 net emissions, CO2 transportation and storage, operations and maintenance, and labor costs. They can actually be divided into groups. The first group is hourly variable, and the last 2 are hourly fixed. So we decided to focus on the first group to find out that our technology, since it is more efficient, leads to lower gas consumption and even to lower levels of emission, compared, of course, to the alternative with higher fuel usage and higher emissions. So we can easily imagine the final results. Considering a one-year period of operation, our technology was able to generate a net revenue of 56 million euros compared to the alternative that performed negatively with minus 124 million euros. On the other hand, in case B, we can see that both technology had negative results, but still our technology was less negative compared to the alternative. Any other additional revenue scenario that we created confirmed what we said so far. And even performing the sensitivity analysis, having as an object gas price and ETS, we found out that being our technology more efficient, it's even less affected in its performance by the volatility of the variables. So to sum up, basically key drivers for case A were energy efficiency and capture efficiency. Key outcomes for case B where negative profitability, of course, for both solutions, but still a better performance of our technology compared to the alternative. And here are the key conclusions. The SOS CO2 LCOE is comparable to Blue Power alternatives. The NPV remains negative due to the high costs of the SOFC. The merchant configuration, namely case A, shows consistent margin and outperforms the alternative, whereas the peaker plant, case B, remains unprofitable, though technically more efficient compared to the OCGT. We also formulated some policy recommendations to further support and invest in research and development to make the cost of the SOFC to decrease, to create incentive schemes to make the electricity produced through this technology more competitive on the market, and finally to reform the capacity market in order to basically give an advantage to the technology that produces electricity in a low carbon way. So here we are.
Thank you. Thank you. Thank you, Jacopo. Grazie. Okay. So now it's the time for the awards. Okay, you know that we have 2 awards, the Luca Latella Award and the Novelli Award. So this award was introduced some years ago, and the name comes from Luca Andrea Latella, who was a young employee at Eni who prematurely died because of a road accident. And he was very, very cooperative, team builder. And so we introduced this award. You probably know that in many business schools there is an award for leadership. And we didn't do that, and we introduced an award for cooperation, basically, And this award, I want to stress, is not given by us, by the staff, by the professors, but it is given by the students. It is the students, they vote what they think is the students who give the best contribution in terms of generosity, cooperation, helping the other people. So this is the statement: for expressing at the best the values of generosity, collaboration, inclusion, respect for diversity during the Master MEDEA 24-25, giving a valuable contribution to the harmony, very important this word, and good functioning of the class. And this year, the winner of this award voted by you is by far Stefano. Okay, so Stefano took really a lot of votes, a lot. Okay. So the second award is the Novelli Award. Luciano Novelli was a former colleague of us. He worked with Eni, he was top manager in Eni, and so he came to the school when he retired and trained generations and generations of students. He was a geologist. And so several years ago, we thought of introducing this award, for the best project. So this year we had 13 working projects, no? So they were very good on average. So choosing was not simple. At the end, one must be chosen. And the winner is the analysis of storage assets bidding strategy in Italian power market. So, Ludovica Bindi, David Boanga, Emanuele Gasli, Enrico Lombardi, please come here. Okay, now is the moment. Magari, allora, I would do this way. I will call your name, and Marcella and Giulia will give you the. Yeah. Yeah, you can shake the hands of the student if you can help us. Okay. Okay. C'è una catena di montaggio. So let me say that these degrees are all full degrees, no? So there is no failure. So that is not always the case. So class did very well. I start by calling you in alphabetical order. So Giulia Fiorile. Fiorile. Yeah. Vedi. Ok, grazie. Vittoria Anelli. Anes Baizid from Algeria. Tagandur Diatamamedov, Turkmenistan. Gulnar Atashova, Turkmenistan. Riccardo Bartiromo. Leonardo Bertolini. Davide Bianciotto. Ludovica Bindi. In our ranking, Ludovica is number 3. Alessandro Bonaveri. Davi Clement Buanga, Congo. Federica Caccamo. Paolo Caldieraro. Giguiba Mussa Camara. Ivory Coast. Antonio Campanale. Giuseppe Cesarano. Teresa Ciazzaro, Messico. Costanza De Filippo. Chiara Facchinetti. Ari Gantora, Indonesia. Emanuele Gazza. Manuele is number 2 in the ranking. Loisos Georglades, Cyprus. Alberto Giovanardi. Antonino Gucciardi. Fabio Inzirillo. Representative of the students, very important role. Aigerim Kadesheva, Kazakhstan. Natali Kaiser, Cipro. Enrico Lanzillotto. Ludovico Lombardi. Maria Caterina Londei. Carlos Alfredo Lopez Orozco. Representative of the students. Stefano Mangione. In the ranking, Stefano is number one. Maddalena Mariani. Yuri Martinelli. Leonardo Massarutto. Grazie, bravo. Manuele Miniello. Oh, grazie. Emanuele Mirabella. Bravo. Emanuele Morvillo. Georgios Papastavru. Sì, proprio. Daniele Paris. Alessio Pesciaioli. Jacopo Pietraroia. Mauro Pignalosa. Jelul Rahil. Algeria. Okay. Luca Reiteri. Muhammad Rivaldi, Indonesia. Elena Rossi. Margherita Salusti. Pietro Santamaria. Sergei Shulga. Mariam Tala. Egitto. Giorgio Torraca. Last but not least, Vania Trander Kostadinov. Okay. So thank you all. That's the end of the ceremony. Let me remember that these are not the formal degrees, because the formal degrees are released by the rector of the University of Pavia that will require some months. But for our ceremony, that is the end. Now there is a light buffet outside that we can stay together. Grazie, grazie a tutti. Grazie per il sostegno logistico. Sei riuscita a prendere complicatissimo. Bravissima. Sì. No. Quel richiamo alla passione, no, da un termine. Motivation. Sì, tantissimo. Va bene, va bene. Allora, dai, sono felice. Anzi, mi è venuto in mente che avere un proprio perché lui posto lì è stato fatto un dai ho fatto il corso con lui. Allora, direi che quando mi ha detto manca un diploma, il mio terrore quando mi Yeah,